So this is continuing from what we did before. We looked at combining two systems. So we considered I have two systems, 1 and 2, which have certain numbers of microstates depending upon their internal energies, and we allow them to exchange energy with each other, but we thermally isolate them from the outside. Okay? And the last condition we derived last time was that the most probable value of U1, we had that d by du1 of the log of W1 is equal to d by du2 of the log of W2. And I also said that in the thermodynamic limit, we expect this probability distribution to become sharp. That means we expect that the value of U1 is almost certain. So in the thermodynamic limit, we expect that the probability distribution will become sharp, so there will just be a single value probability, a single value of energy, somewhere here, which has a high probability. And therefore, if we join these two systems together, the equilibrium value of energy in the first system will almost certainly be this, because the probability distribution is sharp. So I'll call this equation star because it's quite important. Okay. Now I mentioned just briefly at the end of last time that if you imagine you join these two systems together and you allow them to exchange energy, what should happen is that they should reach the same temperature. So there should be a relationship between star and the temperatures of the systems. In other words, star should be equivalent to the statement that T1 equals T2. So that was the last thing I said last time. So we expect this statement star to be equivalent to the statement that the temperatures of the systems are equal. So we expect it to mean that the temperatures of the systems are equal. Now, how can we get that result? How can we make this equation? How can we relate this equation to this equation? Well, Boltzmann made the important suggestion he suggested that we should associate this log of W with the entropy of the system. He suggested the entropy of a system was just equal to some constant, which later on became known as the Boltzmann constant, times the log of the number of ways of arranging that system. So this is a very important equation. Let's put a box around it. This is actually the equation that Boltzmann has on his gravestone, if you visit his gravestone, because it's his major contribution to physics. Okay. So the entropy, there's a connection between the entropy and the number of microstates of the system. Now, let's see what consequences this has. When we defined entropy, we did it in the following way. We said if you change entropy a little bit, a small change in entropy is equal to the amount of heat transferred in or out of the system divided by the temperature of the system. That was the definition we gave for calculating the change in entropy. Okay. You also have the first law of thermodynamics, which says that if I change the energy of the system by a little bit, then this is equal to delta Q minus delta W, where W is the work done. So if the system does no work, then the change in internal energy is simply the amount of heat transferred. And this is the case that we're talking about here. We haven't considered the case where the systems do work, so the only transfer of energy is the transfer of heat. if delta W equals 0, then delta U equals delta Q, which implies from this equation that delta S divided by delta U is simply 1 over T, and therefore the derivative of entropy with respect to energy when the system does no work, delta W equals 0, is simply equal to 1 over the temperature. So this condition that the system is doing no work is important, and for example in a gas, we've seen that the change in work is equal to the pressure times the change in volume. Okay. So therefore we get that the derivative of S with respect to U at constant volume is 1 over the temperature. Okay, so we've got this equation, and Boltzmann says that we can identify entropy with the log of W. So then, if we use this, S equals KB log of W tells me that the derivative with respect to U when there's no change in work of KB log W should be equal to 1 over T. In other words, d by du of log W is 1 over kBt. And then you see that this is exactly what the equation star is, right? In the equation star, what we have is the derivative with respect to energy of the log of the number of microstates. So that's here, and that's also there. So then we get the result we wanted. The equation star simply tells us that 1 over the temperature of the first system is equal to 1 over the temperature of the second system, and therefore the temperatures are equal. So this is the result we wanted to prove. What we've shown is that when the most probable value of energy when I join two systems together is given by this equation, and in the thermodynamic limit we expect this to come sharp, so this is the only likely value of energy. And what we've shown is that if we use Boltzmann's definition of entropy like this, then that condition implies that the temperatures of the two systems will be equal. So Boltzmann's definition like this gives us a connection between the statistical statement about number of microstates and the statement that the temperatures are equal. So if I just summarize that in words, so with Boltzmann's definition, of the entropy S, what we've seen is that the fundamental postulate, when you join two systems together, implies that the systems are at thermal equilibrium. So the fundamental postulate is all we use to derive the equation star. So this implies that the systems are in thermal equilibrium. So this is the fundamental connection between the thermodynamics of a system, how its temperatures behave, and the statistics of a system, the number of microstates it has. Okay, and critical in deriving this was Boltzmann's definition of entropy. Okay, now before we finish, I just want to make one comment about this, which is important. The fundamental postulate says that all microstates of the system are equally probable. And with Boltzmann's definition, if this is true, then the systems are in thermal equilibrium. Right? But we know from our experience that thermal equilibrium does not happen instantaneously. Right? For example, if I take a hot cup of coffee in a cold room, so originally this is, say, at 80 degrees and the room is at 20 degrees, it takes some time for the temperatures to become equal. Right? It will take, 10 minutes or so for the coffee to become cold. This means that the fundamental postulate is not always true. Okay? It takes time for this to become true. Originally, the system is out of thermal equilibrium. That implies, working backwards, if the system is out of equilibrium, is out of thermal equilibrium, then the fundamental postulate is false. Okay? In other words, the probability of microstates is not all the same. So this fundamental postulate, then, is only true if you wait long enough. Right? If you wait long enough, then the temperatures become equal and this becomes true. Okay? But it's not instantaneous. So this fundamental postulate is only true if you wait long enough. And how long is long enough depends upon the system you're looking at. So for example, the coffee, it will take about 10 minutes. Okay? But if you're talking about a system like, a massive body like the Earth, then it will take an enormous amount of time for thermal equilibrium to be reached. Okay? So this postulate is only true if you wait long enough. It's only true for systems in thermal equilibrium. And that means that what we study in this course, where we assume that this is true, is known as equilibrium statistical physics, or equilibrium equilibrium statistical physics, let's say. In other words, by assuming this postulate is true, we've assumed that the system has had enough time to thermally equilibrate. Okay. There is also a very large body of physics on non-equilibrium statistical physics, so how do systems behave when they're not in equilibrium? But although it's very interesting, we won't talk about that in this course. Okay? So in this course, we will only study the equilibrium case. That means we will only study the case where we have waited long enough for this to become true.